So today I'm gonna study the topics on C++. I forgot to open the steps to study on stream. Before I start that, I think I'm gonna do some typing practice, listening to some music. Yeah, so the first one is study the topics on the notebook file, which is this topics here. And I think I'm gonna do a combination of watching videos and uh, reading the libraries and reading documentation. Maybe code trying to not trying to using the Visual Studio thing and reading the stuff on Visual Studio. I found really confusing to set up Visual Studio. I wasn't being able to move around the things, so maybe I'll have to study that as well. I think I'm gonna focus more on accuracy because it seems like I've hit a cap. I can't go any higher on the speed, and I think it's more important to focus on getting the keywords, the not keywords, I'm not sure that's how you say it, but get the words, the letters right, correct, improve accuracy. Slow down. The harder I try to type faster, the slower I go. Usually, when you just focus on the word you're writing, it goes a lot faster. I think that was probably the best time I ever made. It's obviously a lot easier without the punctuation and numbers. I think I'll listen to one more song and then I'm gonna start the C plus plus stuff. I kind of feel like listening to this. So I might read some libraries as well. Yeah, I think I'll search around and I think STD is a library. And this operator, I think it's gonna be a little bit hard to find. So maybe when I'm searching for what is this and how it works, then I'll listen to music and read the documentation and stuff like that. And then the other parts are probably we need to watch videos about it. But maybe I can just read the documentation as well. Then pointers and references, it's probably better to watch videos. Maybe I can change the name to reading stuff. Namespace is designed to overcome this difficulty and is used in addition as additional information to differentiate similar functions, classes, variables, etc. The same name available in different libraries. Using namespace, you can define the context in which names are defined. In essence, a namespace defines the scope. C++ has a standard library that contains common functionality you use in building your applications, like containers, algorithms, etc. If names used by these were out in the open, for example, you define a Q class globally, you'd never be able to use the same name again without conflicts. So they created a namespace standard to contain this change. The using namespace statement just means that in the scope it is present, make all the things under the standard namespace available without having to prefix standard before each of them. While this practice is okay for short example code or trivial programs, pulling in the entire standard namespace into the global namespace is not a good habit, as it defeats the purpose of namespaces and can lead to name collisions. Um, Allows the use of string and bool, string bool int operators. So I was studying some videos yesterday about machine code and electrical systems, and now I think I understand a little bit better how it works. You basically have the transistors and these electrical signals that people design in some way. And yeah, I also saw that Bill Gates, when they started Microsoft, he started programming at 15, I think, and they were doing stuff on paper, which is kind of crazy to think about, because it wasn't that long ago if you think about it. So the guy probably really knows how to code. Uh, but yeah, I think it's pretty much you, depending on the way that you arrange the electrical signals with transistors, you're gonna have the hardware, and then in the hardware, I think that's how it works. You can probably code the operational system, because my main question was how do you get from the hardware itself to the first programs that uh, appear on the computer in the screen to make everything work. Like, what's the moment that the transition happens? And I was thinking about this because with Windows 10, it's interesting to me that they have control over your system. And I was thinking about if I change to Linux, if I buy a computer from that has a Windows as operating system, and then I change to Linux, uh, does this makes the Windows not have access to my computer anymore, or not? That was the question I was asking in my mind, and I think that the answer might be yes and no at the same time, because I think there might be ways to design the hardware so that the company that desired the hardware always has access to what's happening on your computer, because I think that's what's happening. That's what happens in the beginning. You design the hardware, then depending on the way that you design it, and you're gonna have coded instructions inside of the hardware at the initial setup of the computer, and then those instructions are gonna be what determines what the compiler will do, because they will be directly machine code in the memory, and then the CPU is gonna have the coded instructions in the hardware, the initial coded instructions, alongside with the memory. So the memory is going to be a list of the initial instructions, depending on the way that you set up the logic gates. And those initial instructions are going to be read by the CPU, which is also coded in the hardware initially. And then they will become compiled and become assembly. And after they become machine code, they become assembly. And then those instructions show up on the monitor screen, depending, because the monitor screen is just a 2D array with 3D dimensions because of the RGB colors. So each pixel has 3D potential colors, and then depending on the flow of the electrical signal, is gonna configure this whole array. So that I think that's the initial part of the when the system is just initializing. It's gonna be all of that's gonna be coded directly in the hardware, and then it's gonna show up. Whatever is coded in the hardware is gonna show up on the screen, along with the mouse, which is the other another input, and the keyboard. And then from that initial setup, which is the operational system, which is basically translating the hard-coded stuff on the hardware initially into compiler, into assembly, into the stuff you see on the screen. And then from that, you're gonna have, depending on which system is the operational system, you're gonna have a bunch of functionality that's built on top of that. That then it becomes the software, and then becomes the letters you see on the computer. So I think that's the flow of information. So I think the closest thing to the actual electrical signals that transform themselves into information is obviously the hardware and the way that is designed, the logic gates. But then right after that's probably machine code, which, and that's the question that I think I'm not really 100% sure, is that the first initial part is really hard to understand because it seems like magic. We have a bunch of stuff on a, like a thing of silicon, and then it becomes like information somehow, which is kind of crazy. So I think the only way to understand that is understanding machine code and hardware design. And the reason why I'm curious about this and I want to study is so I understand, because I think it's a loop. So machine learning is pretty much closing the loop on itself, where you have electrical signals being transformed by the hardware into information, depending on the way that you design the transistors. And then on top of that, you're gonna build a bunch of abstractions, which is code, and then you're gonna use that. You're using that code to predict the data itself. So it's kind of like what's happening with the human system as well, at least from the scientific paradigm. We have a bunch of electromagnetic signals from the environment that get into the body, that influence the body somehow. Those electrical impulses become the regulation of hormones, and they send signal to the prefrontal cortex and the motor behavior and all this stuff. And that thing becomes a simulation where it's trying to predict the electromagnetic field itself, closing the loop. And I think the computers are an extension of that. So that's why we built them. It's kind of like we're emulating what we do into something else, which is really interesting. And I think understanding how the loop closes on itself is in order to understand how to better design machine learning systems, you have to understand at the beginning how they are transforming, like what is actually happening when you have a bunch of transistors, like both from a chemistry point of view in the material itself, but at the initial stage when it first becomes something that we can understand, a set of information, to then understand how the data you're feeding to machine learning systems is going to be, it's going to affect the system itself. So yeah. So I think I might have to. I'm probably gonna do this stuff on stream to understand the hardware design. Is the thing. How the first set of instructions is built on the hardware itself and what can change. And also, I saw there's also different computational systems. Obviously, quantum computing that everyone's talking about, but there's also another one that they didn't know, which is ternary, which is supposed to give three options instead of two, like binary. And the implications of that will would be interesting to know as well. Variables in C++. Variable providers name of search capper. Basic types of variables. Interval char flow. And I also think that learning this stuff is a lot more important than learning languages itself, because I've realized that it's pretty much first principle thinking, or because it's a lot better to understand the principles themselves than to try to understand the specific languages, because the languages are going to change very often depending on the application. But if you really understand the principles behind it, then it's going to be really easy to learn new languages on the fly, because they're all going to follow the same principles because they are built on top of the same paradigm, which is what I felt when I was learning C++ there. Like, some things change, but it's not that big of a change. And the deeper you go, the more you understand how the abstractions are built on top of, which makes you a better coder, better programmer overall. Because programming is really about solving problems, transforming complex problems into set of instructions. And everything else is just uh, detail. So I think a better way to search for this, because it's gonna be hard to find it. Fundamental libraries probably on C++, and how to study them. I think libraries is written like this. C++ standard library can be categorized in two parts. The standard function library. This library consists of general purpose standalone functions. They are not part of any class. The function library is inherited from C. So I guess C is C++, then C, then assembly, then machine code, I think. The closest ones to. There's also R that the guy talked about the other day, but I think R is the same level of abstraction as C++, if I'm not mistaken. It wasn't R. I think it was Rust. Yeah, Rust. I think R is at the same level of abstraction as Python, just a library for statistical analysis. The object-oriented class library is a collection of classes and associated functions. Standard C++ library incorporates all the standard C libraries also. Small additions and changes to support type safety. Standard function library. Standard function library is divided into the following categories: I/O, string and character handling, mathematical, time and date, and localization, dynamic location, miscellaneous, wide character functions. The object-oriented class library. Standard C++ object-oriented library defines an extensive set of classes that provide support for a number of common activities, including I/O, strings, and numeric processing. These libraries includes the following: Standard C++ I/O classes, the string, numeric, and okay, but I wanna see them and what they do. So
Come.
if I search for functions, the problem is everybody's gonna talk about the functions itself and not the library. Maybe if I search articles and stuff, because usually articles go deeper than videos. Videos are usually more for general public, and articles are more for in-depth study. I also think, yeah, here. Yeah, thanks for the follow. I think Onigumo 69. Is this a video talking about? Oh, it's piano. Nice. I'll add it to the list here. Oh, maybe I can, because the list is from one of my channels, and then I have it on another one. Oh, I can add here. I think I'm gonna close this window honestly because you're probably not gonna talk about. It's just documentation to see what each thing does, but it doesn't explain anything. Which probably isn't the point of the thing anyway. Container braces, C++ are containers, blah, blah. So how can I search for this? The video you shared? Or you're talking about searching for videos about the standard library? I did a course on, I think, Code Academy, and then I used the stuff. So I think I understand the surface level concept of how it works. But the videos I only found videos that explain the basic stuff and not how the library works. Like, I don't want to know how to use standard library. I want to know how it's built and how do I search for this. The link you shared opens up a piano video for me. This is why is Wonder Woman. It's a piano video. All lengths are instruments. Can use the C++ in them. Yeah, that's a good way to look at it. Yeah, I get what you're saying. What do you think I should do? Something that is not really hard to implement first. The thing is, I don't have. I don't know. Let me see this link. Yeah, I get what you're saying. So what I want to do is build my own library. I have the steps here. So this is my plan. And the reason why I'm concerning myself more with understanding is because I'm not too much. I guess it goes hand in hand, right? If you learn how to build stuff, you are also gonna be understanding more of the language. But I'm not really, at least on the surface level, I'm not really concerned about the practical so much because I think I have a good grasp of how to put things together. Like, yeah, I'm not gonna be really good, but then I can research everything, like how to build this function this way and stuff, and I'm gonna learn a lot doing that. But I want to focus more now on the principles and theoretical part of the language to understand how everything, like where things come from, because I'm also doing the practical stuff off stream as well. So it goes hand in hand. CPP reference has all the details. It will makes more sense as time goes by, but pretty abstract in the beginning. Yeah, I already feel a lot of improvement though. Like a couple of months ago, I didn't know anything, and now it feels like it's kind of setting in, setting the concepts and stuff. So do you suggest going one by one here, or Is there a specific one that is good to start? Preprocessor, expression, declaration, and initialization. Search standard library here and see for yourself. Yeah, gonna do it. Thanks for sharing this stuff. I think I'm gonna do it on another page, so I have this one. Namespaces. I think probably the main priority I have now is understanding how the code affects the memory. And because I know it's important, it's not that important, but it is important. The memory allocation and how the computer reads the instructions and where is stored in the computer. And I have a surface level understanding of that, but I want to get a deeper, more intuitive grasp of. So when I'm coding, I have that in the back of my mind. Learn CPP. Great. Oh, that's nice. So I can go one by one here. I assume this is a book. Yeah, I'm gonna read this stuff. This seems nice. Just going through it like this first to see roughly what it talks about. Also understanding the terminal. Understand everything pretty much. One step at a time. And the Chernos tutorial series. Yeah, I'm watching that off stream. I watched a couple of them. They're really good. I heard about the Cherno and the LED something. So I think I'm gonna read this and I'm gonna search here for standard library. Basic concepts, keywords, preprocessing, expression declaration. I'm probably gonna put this on the favorites as well. Don't forget about it. Chili tomato noodle on YouTube for really deep understanding. Nice. I'm gonna subscribe to them. Yeah, that's what is hard to find, right? Like the easy stuff, a bunch of people make videos about, but as you go more specific, is there's less interest, so people make less videos about it. Do you recommend some playlists as uh, the first one that I should watch? Yeah, C++ multi-threading, coding challenger, C++ advanced C++ programming, advanced C++ direct game, intermediate, C++ STD jams. That looks interesting. C++ intermediate and advanced. I think I'm gonna watch the STD jams first. Then I think you're talking about intermediate C++ DirectX game programming tutorial series. And then advanced. I don't see one that is advanced, but without programming, without game programming. So but I think I'll watch this playlist off stream. Intermediate. They're all pretty much the same. In the end, it's just a bunch of math. Exactly. No matter what programming. Math and physics is everything. Pretty much. The goal is draw pixels on screen or send a packet from server to client. Yeah. So function statement, class overloading templates. Headers, names, requirements, future test macros, language support library. Sure. I'm gonna go to the bathroom before. Yeah, thanks. They seem really good, honestly. I think I'll start by this one because it seems like more easier to read. I'll start with this one, then I'll search here a little bit. I'm going to the bathroom real quick. Have to pee. CPP preference is the dictionary of C++, just literally for reference, not for learning at the beginning. So, but I'm gonna leave it open because I'm probably gonna use it later. I'm gonna start with this stuff here. I'm gonna play your music from the beginning. I'm gonna read this. Then, when the music's over, I'm gonna stop, make some more coffee, and then continue to play music and read this. And probably read out loud some parts. And thank you for sharing this. Yeah, it's really good stuff. Probably saved me a lot of time researching. Oh, you wanna watch the video? Not just listen? If you want to, I can watch with you as well. Doesn't really matter. Just 5 minutes. Not that big of a deal. Sure. I love this kind of music. Yeah. It's crazy. It's like they're telling a story or traveling back in time. I'm gonna search for a few cool music from her. Try to show the playlist. Yeah, it probably takes a lot of practice to be like that. I wish I could play. Maybe someday I will learn piano. It's like string theory. Kind of like you're connecting to different universe, let's say, in state of mind. I think this one seems interesting. I think I will get this one and the other one to add to the playlist. Not sure if I added the other one. Yeah, I did. Uh, since you're interested, watch this one. 2 minutes and we study hard. I'm gonna watch this one. After this one that you gave, I'm gonna make more coffee and then I'm gonna read this stuff. Let me burn the bots. Oh, it's a lot. Yeah, that's awesome. I'm gonna go make some coffee now, and I've added to the playlist here. Here. And you said you're going to sleep, so you're probably not gonna be here when I come back, but yeah, good night for you. And thank you for sharing this stuff, man. It's gonna help me a lot, probably. And I'm gonna read this thing, string while listening to the music, which I feel like doing today. Yeah, good night, man. So I'm gonna make I'm gonna do a detox from coffee next week, 1 or 2 weeks, I think. Not drink. Today's last day that I drink coffee. I'm gonna eat this stuff before I start reading the book. I'm probably gonna change the title of the stream. Maybe I can watch a video actually while I eat. Probably do that.
Hey guys, it's Chili here. Welcome to a brand new series I like to call STD Gems. This series is going to be introducing some, useful little nugs from the standard library. You can expect short videos focusing on a few related tools from the standard library. You can expect tons of jokes about STDs because it's relevant to my interests. Mainly, I'm going to be focusing on stuff from the algorithm library, especially to begin with. It's just a great toolbox for building your own custom algorithms, and I think it's underutilized. A lot of people don't really make full use of the great tool that you get there. So I want to teach you guys this. I want to turn you guys into the kind of C++ programmer that's going to get the good old upnod from other professionals. Now, though I do plan on essentially covering everything from the algorithm library here to start off with, there are a few exceptions. There are some things that I'm not going to cover, at least to begin with. It's not going to be within the scope of this series. And those things are, well, first of all, these execution policies, I'm not going to cover them in this. They deserve their own video probably, and I don't think they're implemented yet. I might be wrong, but they're not implemented definitely in all compilers. So support is still spotty for these guys, and it's really its own beast. So we're not going to be covering these guys. I'm also not going to be covering this uninitialized memory stuff. They're really outside of the scope of what I'm trying to do here, which is just teaching tools for building general algorithms. I'm probably also going to be skipping stuff that's marked C++20 because, that's not really here yet. So this stuff will be skipped, but there's not that much of it. And again, these out-of-order numeric operations, they're kind of the same idea as the execution policy stuff. It's parallelization stuff, and it's not really in the scope of this video, so I'm not going to be teaching these guys either. But we probably will be, dipping into some stuff from C++17, and so to be able to follow along with that stuff, you're probably going to need, Visual Studio 2017, or, you could even follow these videos with GCC or Clang. Although this series is mainly about algorithm, I'm also going to cover some stuff outside of algorithm, like, for example, in the containers. Some of the containers that I haven't really covered, Array and DQ, might give them their own little videos. Also, the container adapters here, they'll fit in nice in this series. What else here? Random. There's a lot of interesting random distributions that I haven't gone over, so I'll cover a few of the more useful ones. Some of the things that I'm not going to be covering here, for example, threading or shared pointer, because really those things, they deserve their own dedicated video in a main series, or even their own arc or their own series. Like threading might even become its own video series by itself. So those will definitely you won't see them in STD Gems. But what I might put in Gems is little previews of stuff that's up and coming, like ranges or concepts. It won't be a full-blown explanation tutorial, but it's just a little taster of things that are still in the experimental stage. And yeah, the basic way that these videos are going to go, I'm going to explain the mechanics of the tool. I'm going to give some example of how you use the tool, and I'm also going to give some descriptions of real-life usage scenarios so that you can get a concrete idea of how this stuff can actually be used. Because I think that's one of the most important things a lot of tutorials leave out, is they show you the how, but they don't really tell you why you want to know this information. But yeah, I hope you enjoy these videos. I want you to watch them, become a master of the standard library, and then you can call me out in my comments whenever I, miss an opportunity to add another STD to my code. I hope you guys are excited for this. If I could get you to click the like button for this video, probably help it out a little bit since it's the first video in the series. It'll get better search ranking on the YouTube, Google machine. And I will see you soon with some more STD Gems. Hey guys, it's Chili here. Welcome to STD Gems. This is a new series that I'm doing here. It's going to be some bite-sized videos where I introduce some cool and useful stuff from the standard library in every episode. So today, and for the time being, we're going to be looking mostly at the algorithm library. And there's a lot of stuff in the algorithm library, obviously, but we're going to break it down step by step, little bite-sized chunks. We're going to cover a bunch of related stuff today. We're going to cover the copy-ish stuff. So these guys here, that's the topic for today. Std copy, you might have seen me use it in videos. It's pretty goddamn simple. You give it a couple of input iterators defining a range, like this, and you give it an output iterator defining the start of the destination, and it will copy from that range into the destination. It's pretty simple. Let's take a look at the code in action. We've got a couple of containers here. I'm going to write those containers out just to show you what they contain. I'm going to run the copy, and then I'm going to write out again. This function here, write to cout, is a template function, and I'll talk a little bit about it later on. But right now, all you need to know is it just fires out the container contents to the console window. And if we run this, you can see here we've got our containers here. They contain strings that are words and digit representations of numbers, and we're copying from the first one into the second one, and here is what we get. So it is fairly straightforward here. We give it the range to copy from, we give it the place to copy to, and it will overwrite what is in those places from the source range. Now, one interesting thing about copy is the source and the destination, they can actually be in the same container. There's only one restriction, and that is that your destination, it can't fall within the range of your source range. So it has to be outside that range. But as long as it's outside that range, copy is going to work fine in the same container. So here you can see my source range is at the beginning of B. My destination start point is just a little past the middle of B. And if we run this, we can see that, yeah, we're copying the beginning of B into here. So we're duplicating that part of it inside the same container. And that's fine. If you put the destination inside this range, you're going to get a little bit of a weird result. So here we see that we're duplicating it, but we actually triplicate the 0. And that's because we're writing into the source while we're also reading from the source, so that 0 actually gets copied twice. There's a way around that. I'll talk about that in a little bit. So you can copy, overwrite the contents of a container or whatever. You can also use iterator adapters to do things like insert. Using copy, you can insert into a container, but I don't really do that much because containers like std vector, they have an insert operation that takes iterators and it does the same thing. So there's really no point to bring std copy into the equation there. So let's say you want to insert or append a bunch of values to cout. Well, you don't have an insert method. You can't really do it that way. But what you can do is you can use this iterator adapter to create an iterator from this stream. And then you can use std copy to copy from your container into that stream iterator. And that's what this function here does. It takes a container, and it also takes an optional delimiter here, and it will copy the whole contents of the container into cout, and it will use the delimiter that you give it as separators between the values that it copies in. So that's what we're using here, and it's a neat little thing you can do with std copy. One thing you might notice here is that the OStream iterator, it requires the type of the value that is going to be inserted into the stream. And with a container, this template, we're only templating on container type like vector. We're not directly templating on the type of vector. So you can use these little helper type defs that are defined in your containers to get the value.
Right back. Yeah, so far from this video, I think it's a little bit too advanced for me still. I'm gonna watch the rest of the video now that I started. And then after that, I'm probably gonna watch it again at some point after I read all this stuff. And then when I finish this, I think I'm gonna read the thing, listening to piano music, which is perfect because I feel like listening to some music today.
You type and use that. There's little things you can use to make your template functions and template classes. You know, I'm talking about these guys here. You can find them in the documentation for your containers at this point here. Now, C++11 gave us a little boy called copyn, and this one is a lot like copy, except instead of taking an input range, it takes just an input iterator and then a number of elements to copy. So that can make your life maybe a little easier instead of having to, you know, do this little iterator arithmetic bullshit. You can just say, well, you know what, just give me 4 dudes
I
starting
like his style so far.
from here and put that out there. And we just go copyn. Let's change the range to be something that is valid. Yeah, we get the expected result. So it's a little bit of shorthand, saves you a little bit of typing, maybe makes it a little clearer. Now, copyn can also enable you to do things that wouldn't otherwise be possible. Let's say I want to copy 5 values from cin, std cin, into a container. How would I do that? Well, I need an input range, right? The first one is easy. That's just your input adapter. But what is the second? What is the end part of the range? Would it be, you know, input plus 5? No, you can't do that because the type of iterator that you get from this adapter doesn't support this operation. It's not a random access iterator. So how do you get the end iterator? Well, you can't. But what you can do is you can go copyn, give me n things from this input stream, give me 5, and jam them into B.
Right back.
And if you run that, now we can get 5 things. So let's put 5 things onto the stream, press enter, and there you go, jam them into our container. And you can do that. I mean, it's not super useful for console input, but it could be.
So yes, what he means by container is these 2 vectors here that are initialized with these strings.
Very useful for things like file input. Now, copy backward does the same thing as copy, but it does it in reverse order, which is sometimes important. Let me show you what I mean by reverse order. So with copy, normally you're going to copy, it's going to copy this one here, it's going to copy this one here, so on and so forth. But with reverse copy, it copies this one here first, then this one, then this one. The end result in this case would be the same either way. The order is just reversed. Now, sometimes it does make a difference. So let's look at the case again where your destination start is within the range of your source. So you copy this one, it overwrites here. Then you copy this one, you get a B. Now you're copying this one, you get the overwrited A again. So you triplicate A. Now let's try this in reverse order. So in reverse order, we're going to copy C. So C is going to go here, then B goes here, then A goes here. Look at this. Now you don't get the triplicate A if you copy in reverse order. So if you have overlapping source and destinations, it pays to copy in reverse order. If your destination start is within this range. If your destination start was here, you would want to use a normal copy. To me, copy backwards isn't that interesting because it's basically redundant. You could achieve the same effect by using rbegin and rend to get reverse iterators and then using normal copy with reverse iterators. In fact, you can see copy backward probably does that because it requires bidirectional iterators, so it has to reverse them either way. Now we come to copy if. Copy if is probably the most versatile in this whole set here. It can be used for filtering, which is something that you do all the goddamn time. So how does it work? Well, you give it an input range and an output start point, but you also give it a predicate. And what it does is it checks every value against this predicate, and it only copies if it passes. If it fails, it skips it. And this can be great for filtering. So let's say I got a couple of strings here, and I want to get only the capital letters. I want to filter them out, and I want to get them all into a single container, into a single string. So what I can use is I can use copyif as a filter here, and copy from these strings using back inserter, append them to the end of my destination string. And my predicate is going to be std is upper, which just checks to see if a character is an uppercase character, and that can be found from CC type. So if I run this, here's my two input strings, and here is all of the capital letters collected here, filtered out from these two strings. Pretty simple, pretty clean, pretty sexy. Now, let's say I want to copy some strings from A to B, but A is going to be destroyed anyways. So, I mean, what happens when we copy these values? When we copy a string from here to here, it's going to create a new string as a copy. It's going to do a memory allocation, and then it's going to put that in this place in the vector. It's going to replace this one. But if this A is going to be destroyed anyways, all these strings are going to be destroyed, we don't really need to do a new allocation. We could just use these strings, move them into here, and we could save ourselves some effort. How do we do that? Well, algorithms provides us with move and move backwards, which do the same thing as copy and copy backward, only instead of making a copy, they just move the content. So we do std move from A to B, and I'm going to write out A and B afterwards to see what happens to both of them, and a little custom delimiter on A to make it easier to see what's happening here. So we run that, we see after we do the move, 0, 1, 2 has been replaced here just like a normal copy. But what happens to A is 0, 1, 2 actually get pilfered. So those strings become empty because, I mean, their content is no longer there. It's been moved into B. So that's the difference, and it can make things a lot more efficient, or in some cases, it can make things possible that weren't possible before, because as you know, there are many data types, like for example, unique pointer, that cannot be copied, but that can be moved. Now you might be wondering, okay, well, where is move if, or where is, move n? And they don't exist. So what happens if you want to, do a filter, but you want to move instead of just copying? Well, you can do that. You just got to be a little clever about it. So let's say we want to move from A to B, but we want to filter and only move those strings that have a length greater than 3. So how do we do that? Well, we start with copyif because that's what we need in order to do filtering, but that will do a copy, not a move. So what we got to do in here, std make underscore move iterator. So we take our normal iterators, we turn them into move iterators. We got to do that for both iterators in the range, because we're going to be iterators got to match up. And so we're going to be moving from this range, and the destination is fine, doesn't have to be a move iterator. So we just go b.begin. Actually, what I want to do here is I want to go a.end because I want to go over the whole thing. And now, still angry because it needs a mother trucking predicate, right? So the predicate is going to be, so we take in a std string, we'll take that in by reference, we'll call it stir, make it const because that is my fetish, and we just want to return stir dot size greater than 3. And there you go. That should be everything that we need. Let's save, let's build, see if we get any errors. We don't get any errors. Here you can see we have performed the filtering. All that remains in A now are the guys that have a length of 3, and these ones have been overwritten in the destination. Now, what you might notice here, and what might be, you might have been expecting that, for example, here would be 0, and then there would be, digit 1, digit 2, and then we'd have the word 3. But that's not how it works, because when you skip over something in the source, it doesn't advance the destination. The destination stays the same. So you're going to have all these guys in line. That's one thing to make note of about how copyif works. Although personally, when I do copyif, I'm usually appending to the end with a back inserter instead of overwriting stuff. But there you have it. And so here we see that actually move and move backwards are both also kind of redundant, because we can get that same functionality and more by using iterator adapters, but they're there if you want them. Another thing you might notice here is after you move out of A, it's got a bunch of these empty husks just left in it, stinking up the joint. And that's fine if you're just going to destroy A anyways. All right, let me give you a real-life example of how you can use copyif. So I got a vector of poos, and what I want to do is I want to select one poo at random from that container and use it for something. But I only want to select poos that are stationary. So what I do is I create another container, and it is of reference wrapper to poo. And then I copyif from my container of poos into the reference wrapper. And what this is going to do is when I copy from here, it's not going to create a new poo in here. It's going to create basically a pointer to a poo. And I'm only copying the poos that are stationary. So at the end of this here, I'm going to have a vector of pointers to stationary poos. And then over that range, I can just randomly select an index and use that pointer to do something with that poo. And that's it for today. That's it for the copy boys. Hope you enjoyed it.
My initial impressions is I really like his stitching style, and he has humor, but he's not over the top with it, which is nice. I'm gonna close here because I have it open on my other browser. And he was talking about iterators there, looping over a vector and copying stuff, which I understood some parts of it, but I don't understand really well the memory aspect and the location he was talking about. So yeah, I'm gonna start reading this now. I'm gonna put the piano playlist that I have, and I'll probably read in silence, and sometimes maybe talk about stuff. Nice. there's always a trade-off between things. Next lesson. I'm gonna close the window a little bit because it's reflecting on the window. No, on the screen. So I think at the end of each page, I might make a comment, depending on the thing, and then I'll continue to listen to the music. So the last page was talking about interpreter versus compilers. Interpreter is basically the IDEs, and some languages only run with interpreters, and the trade-off is that an interpreter, it's easier to code the language, but it takes more time to run because it has to do much more steps. And a compiler, you pretty much are decreasing the amount of steps because you're getting closer to the machine language, machine code. But there can be trade-offs because not all languages run with only a compiler. And then they were mentioning JavaScript and Python, and they said that some parts of Python can be deconstructed through something that can be compiled. But the more abstract you get, the less compiled the language becomes. So there's always a trade-off between simplicity of the abstraction of the language, because you're stacking up levels of abstraction. You're putting together more logic, which allows you to do more things, obviously. But in exchange for that, you sacrifice in speed and efficiency. So there's always this trade-off between how simple you want a language to be and how efficient, so you can build more complex applications. But then you sacrifice a lot of speed and flexibility, probably. Kind of like using libraries. So let's read this one. I forgot to mention that in languages that are interpretable are better for web browsers because they can be load faster. And compiled languages not so much. Because I didn't understand really well, but sometimes the compiler can make worse code because it doesn't have an understanding of the whole program when it's running the thing, and the interpreters do. They have a better understanding of the whole thing, so sometimes they are better when you need stuff to be loaded quickly, as far as I understood. I hope they talk about the how it works, everything, not just giving. From so far, from what it seems, it feels like they're gonna talk about it because they're more focused on the fundamental parts instead of just giving the instructions. Nice. So they're basically saying exactly what I imagined, which is that C++, unlike other languages, it's because it's lower level. I think it's lower level that they say. You have more control and flexibility over the memory allocation, but that obviously can be bad because if you don't know what you're doing, then you're gonna make things worse. As if on the other languages, because it's built on top of these lower level languages, they have the nested abstraction inside the stuff, inside the methods and all of this stuff. So you gain speed, but speed on writing, but you lose control and flexibility to be able to do the things that you want. And that's why C++ is better for more when you need speed and efficiency and flexibility. So probably for engineering stuff, C++ is a lot better than doing Python. But the reason why people don't probably the reason why people don't do it that much is because it's probably harder to write the code, and because I suspect that you're gonna encounter a lot of bugs that don't necessarily show in your code. Your program still runs, but you because you design it poorly, it's not gonna do what you wanna do, what you want it to do. So it's probably harder to debug. But I think that the clear path is to eventually just do things with C++ because it's probably a lot more efficient. Yeah, I think that's all that I thought about the last page. So here it makes sense because it's 80-20 rule. So it makes sense that 20% is going to be spent building, and then the other 80% is the difference between good and bad programs. So just talking about the very basic stuff in the beginning, about CPP files and using a code editor. So it's very basic stuff. And one thing that came to my mind that is not necessarily, it is related, but not that they didn't talk about, is that in a way, when you write program, you're using information to change the state of electromagnetic field. So maybe all the computation is just the shaping of the electromagnetic field in relationship to information, which might have a relation to the way that a space time is shaped, because nobody really knows what information really is, and from computers it seems like it is a configuration of an electromagnetic field which has gravitational force, because yeah, that's the question, I guess. How are these things related? It seems like it's kind of like a self-fulfilling prophecy where things tend things have a tendency to be the way that they are. So depending on what you're running on the computer, is gonna kind of like attract the same kind of stuff. But there's always a balance because of this symmetry of perception. So it's not necessarily deterministic and not truly random. But yeah, I think the configuration of the electromagnetic field with information generates gravity. And that's, yeah. So it's very interesting. The deeper I go, and the more clear that these things uh, become in my mind, the more connected everything becomes. All these concepts from everything else. And it really is really crazy that you can do that. You can put a bunch of chips together and then run some voltage through them and come up with a whole new universe, pretty much. Which also is kind of like a wormhole because you're connecting through different parts of space-time, just use information. But obviously, you're still trapped by the limitations of the speed of light. So, but I think these concepts might be related, which is gravity and information, because if you can replicate the same configuration of the electromagnetic field with information, you can essentially break the distance in space-time, but it's still trapped by light because information travels through light. So it might be that, but it might be the case that space-time, it's just that a space-time is defined by the limitations of light, but the dimensions underneath space-time that gives rise to space-time live on the complex plane, and they are the information sources from which reality transforms itself over time. So I think all these things are related. I'm gonna keep reading this stuff. I'll open up the Visual Studio for when they have examples. I'm gonna try to do them on the side. I also just got an idea that if all languages are pretty much set of instructions built on assembly, then you can probably create your, obviously you can create your own language, but never thought about that all languages are essentially libraries built on top of assembly and machine code. So any language you're gonna use, you're gonna have a predefined set of libraries that dictate the rules of the language. And it might be possible for some applications, if you understand the libraries that make up the rules of the language, to change the libraries and gain even more flexibility depending on what you want to do. So you can keep the core of the language, but then if you really understand the principles behind it, you gain even more freedom and control to do stuff that goes outside of the scope of someone that only uses the language as it is would be able to do. So this might be very interesting as well. So I think that I have to at some point also make a go to understand what's the best way to study libraries from languages, to inspect the source code of everything. Because I think that's just much like using Google. It's Google is a very valuable tool, but if you don't know how to use it, obviously it can be really bad as well. So I think programming languages are like Google in that sense, that you have all the information available. But what really differentiates people is their ability to know how to search something on the database. And I think that for programming is the ability to investigate source code and to understand how to get to the bottom of how things are built. So you create increase understanding, and you can debug things a lot faster that way. Which is there's a trade-off where you're gonna spend a lot more time in the beginning learning initially than someone that just debugs using all these tools. But long term, you're gonna gain a lot more understanding, and then you're gonna be eventually gonna be able to just look at the code and see, because you know the fundamental concepts and rules, you're gonna be able to understand why this stuff is not working right away. At least I suspect. So I think that's the approach that I need to have. So I was thinking that in a way everything is electromagnetic field, and different geometries are just configuration of that electromagnetic field. So gravity seems to be information. Gravity and information are the same thing, probably. Because if you think about it, the reason why some objects are the way that they are is because of the gravitational field. And the separation between objects is just an illusion of the reference frame of experience that's creating space-time. So that transformation of the electromagnetic field into concepts creates this quantum entanglement on that field that creates geometry. Just like programming, everything is a very simple field of quantum instability becoming geometrical shapes, which is space-time. And gravity is the tendency of that field to create things on top of what was built before. But there's still the question, which is the question that I've been thinking for a lot for a long time, which is if the momentum of gravity doesn't come from anywhere because it can't come from anywhere, otherwise it would have ended already. The bottom line has to be infinity. So the momentum of gravity, which is the rate of change of the electromagnetic field into information in geometry, which is the illusion of separation, the parsing of infinity in relationship to the reference frame of reality of the now, which is space-time currently. If it doesn't come from anywhere, what decides what's that rate of change? It has to be a distribution because reality is the distribution of the electromagnetic field interacting with itself. But what determines, and if it is a self-fulfilling prophecy, what determines the rate of the self-fulfilling prophecy, which is gravity, in my mind? That question, I don't think it's, I can't find a way to think about it, or to find an answer to that. Because it has to come prior from knowledge itself. So it's kind of like an AI trying to figure out where it came from. It's just gonna create more stuff because it's trying to predict the own field that created it. Yeah, I guess in relationship to what I was talking about, I guess the question is, what's the frequency of information? What determines the frequency of information? Because if the field creates itself, what determines the rate of change at which it creates itself? And where does what's the moment where the some new information becomes the new information from the old stuff? Now then we go into the question of cause and effect and the relativity of events, because everything has to be in the now at the same time that it isn't. So past and future are born out of the same place, and they exist simultaneously. They are co-created at the present moment, and that's what gives the illusion of time passing. But what determines the relationship between them, the rate of that relationship, the density of the frequency of information, which is the same because density and frequency of observation has to be the same. Data and probability is just the paradigm, that the assumption that space-time is continuous, that matter maintains itself across space-time. So even though the geometry changes, the distribution of mass is going to be an approximation of the information in relationship to a reference frame that creates the distribution of probabilities, and that's the assumption that they are that these things are connected, that the probability is equal to the geometry of space-time, of the distribution of mass of space-time. So it is always relevant to the frequency of measurements in relationship to a reference frame because of density. The lower the signal is, the less confidence you're gonna have that something is what it is, because you have less data, and the higher the frequency, the more data. So increase the trust you pass into the system. That, for example, a coin flip is going to be 50-50% because you have 1 million observations that it's going to be 50-50%. But you can never prove that for sure, because if you have an unlikely event, you're never going to be able to prove that because it's unlikely by default. So if you can only observe that event one time in the history of the universe and it happens, you're never going to know if that's the true probability or not, because you don't have time. So the frequency of observation and data and probability are the same, which relates to the density of space-time. Which is why you can never know the arrow of time seems to be information, the reducing of entropy. And that part of reducing of entropy and gravity and how it relates to all of that, it seems to me that is the bottleneck of knowledge itself, and you can only get there with experience. But then if that's the case, it sucks, because that's another thing that I found watching Leo Guru's videos that he doesn't talk about, which is, I agree with him in most points, but if we can't use the paradigm of science to reach common sense, because not everything can be provable, how do we determine in the subjective what we're gonna do? Because then it's just opinions against opinions. And even if you're using facts, it's just opinions against opinions, because the fact is the assumption of the probability that I just talked about, that the probability holds true in space-time because it follows the same rules, which is logic, which is the connection of the experience that is existing right now, which is the illusion of past and future that is being born at the present moment all the time. So through that logic, how do you get to reach a place of common understanding if you can't use facts to determine what is right and what is wrong? It has to be both simultaneously, obviously, because symmetry is always relative, but how do you get to that paradoxical position without having something that you can prove? I think is the question. And I think that's the path to solve the theory of everything problem and to really understand what gravity is. And I think that's, yeah, probably these things are related. Gravity with consciousness or whatever you want to call it. And it has to be an ego, but at the same time distributed. So it's probably a paradoxical point that encapsulates the two. But you understand how it's determined and why it is the way that it is. Like I just can't find a way to think about it. But I guess that's why I'm studying all this stuff is to really understand, try to understand better. And the whole point of AI is the same thing probably that we are doing either consciously or subconsciously to try to understand how the loop closes on itself. And this might be what the singularity is, but yeah, who knows? Another thing that I just thought about the other day is that in relationship to the problem of self-destruction, I thought I had an idea that I think might be interesting, but I'm not sure if it's possible to implement it, which is to, in order to understand the behavior of human beings and social structures in relationship to space-time, the electromagnetic field, and how it relates to AI, it's probably, it might be a good idea to study the boundaries between countries and cities and states, because that's probably going to be a fractal pattern that gives an idea about the relationship between tribes, because that's how the boundaries evolved through time. So the boundaries between countries and states and cities might be a very good approximation of the way that human beings should not choose, but they develop social structures and boundaries over time. Because, like Mandelbrot said, the coastline of countries can be measured by a fractal. So I think that's worth investigating. And I think every boundary is a fractal because at the boundaries you have approximation of infinity. And that's what the definition of the boundary is. Because in reality there is no separation. So the separation between things is just the nature of perception, which is the parsing of the infinity. So the moment the parsing collapses you have a boundary, which is the limit of infinity. And that, and to understand the fractal geometry of social structures, I think it might be a good plan to try to extract these boundaries from the maps. Maybe they have the maps, But then I'm not sure how I'm gonna relate this to the way that the Earth changes and the water, obviously. But I think there, it might be possible to create a program that measures the boundaries, uh, creates a fractal out of them, and then investigate the connection between human beings and the way that it evolves over time. And I think in order to do that, it um, might be it might be necessary to not necessary, but it might be interesting to see if I can also get maps from historical states to see not only the way that it is today, but the evolution of it, because obviously that will give a better chance of having a higher representation in space time of how we evolved through time. But obviously, it's going to be an approximation because it also depends about all the complexity of the universe. But then it is probably impossible to figure out and to take that into account because it's probably computationally reducible. So I don't think there's. I think the best we can do is try to get the approximation and just the core principles of the way that things tend to work and the way that we tend to structure ourselves on land. So we can start to predict what's gonna happen given certain situations on the way that because human beings are probably just like water or any other type of material. It's just a social structure between molecules in the electromagnetic field because it is the electromagnetic field. All the difference between objects is just the relativity of the way that this electromagnetic field is being parsed, which gives this the illusion of separation and the sense of geometrical structures and mass and density. I don't see solution exploration on my Visual Studio. Hmm, nice. Just to remember later. So far, they're just talking about configuring Visual Studio. Um, hey, thanks for the follow, Safari Miner. I'm good, and you? Not sure if you can hear me through the sound, music. Nice. I'm reading this. I think it's a book about C++. If you have any questions, let me know. I'm gonna open up the window a bit because there's less sun now. So far, I'm really enjoying this book. This is exactly what I needed, I think, at this beginning to understand a little bit more of how Visual Studio works. But I'm still, I'm afraid that he's not gonna talk about how the standard library works, and more of the behind the scenes of the language itself. But if he doesn't, then I'm gonna. I think he's she because it's Alex, but maybe it's a she. I don't know. They are gonna talk about it. If they don't, then I'm gonna research it later. Anyways, it's not gonna hurt me to read the book. Only makes the information more. Uh, Makes me retain the information more. So mine was C++ 14. I changed to 20 as they recommend there. So I'm gonna copy this code and try to run it to see if it works. I'm gonna type it out for practice purposes. Maybe I should change the screen that I'm doing this while copy. So I think that's what I'm gonna do. Yeah, this is another thing about about Visual Studio that I found so far. Whenever I drag this screen here, this screen here, the other one doesn't come, the Solution Explorer. And I'm not really sure how to put them together here. It seems like this changes, but it doesn't really work that well. What I was trying. It's weird. I don't know if I'm doing something wrong. Yeah, now it just goes back to the side here. And there probably is a way because I've seen people do it where they put it to the side, but I'm not really sure how to do it. I can only make it if they are separate. So now I'm gonna put the tutorial here and copy this stuff. Namespace. Already have that. Nice. So it works. So I did it the right way. And the applause. Projects. Sport template. this part right here makes me think that, and I didn't think about that before. It just hit me that languages are just like computer languages, and so it might be the case that they have pre-embedded functionality into them depending on their environment. That's why languages change in relationship to people, because they are specific to the environment, because they are a consequence of the way that the brain and human beings interact with the environment. So as a network of individuals learns to adapt itself in their environment, it creates the language that is more specifically useful for that kind of environment. In the same way that different programming languages can be useful for different tasks. The so by learning different languages might be allowing yourself to gain a greater understanding of different problems. And I think these things are closely related: the environment and the language that the environment uses. So it might be the case that there are ways to create different languages that don't exist, that allow us to solve problems. Maybe if we extract the abstractions from all languages and we get to a more fundamental level, kind of like C++ and machine code, we would be able to create new languages that allow us to gain a greater understanding of the way everything works. So that's, I think, something interesting to think about, but obviously it would be very difficult. So not sure how I would go about doing that, because personally I'm not very good with languages and grammar and that stuff. But I think it's a interesting concept. The languages are closely correlated with the way that the environment works and the network that is trying to adapt itself in their environment. So it also makes me think that the more advanced a language is, the bigger the vocabulary, the more mass it has, and the less creativity you have, because it's always a trade-off, just like computer languages. So when using Python, you gain speed. Gain speed on typing the code, but you lose efficiency and flexibility, which means that the higher abstraction a language has, the less creativity you're gonna have when using that language, because you are already applying a bunch of concepts that are embedded into the language itself with a bunch of underlying assumptions. So it's probably harder to break the paradigms with languages that are very advanced. In order to be able to think creatively, you have to break down the words and find the fundamental meaning behind them, and why, and question the assumptions that you are applying when you use certain languages. Just like you do when you program, the more you understand the machine code, the higher the chances that you will be able to understand how things are connected together. Just like with normal languages. I'm gonna go to the bathroom. Right back. So a statement, I think it is a line of code that tells the computer to do something. Instruction, a computer program that tells the computer to perform an action. Function is a sequence of statements. What is the name of the function that all programs must have? Main. Programs run, where does the execution start? At the top. In the library statements, I think. First statement inside the main function. So I was wrong. Starts in the main function. Then calls the libraries, I guess. What symbols are statements in C++ often end with semicolon. What is a syntax error? When you don't type it right, maybe? It's a compiler error that occurs at compile time when your program violates the grammar rules of the C++ language. What is the C++ standard library? Is the std library that allows you to use int, void, character out, and character in, the fundamental functions. A library file is a collection of precompiled code that has been packaged up for reuse in other programs. C++ external library is a library that ships with C++. It contains additional functionality to use in your programs. Not sure about this one. So what's the point of pointers if we can't access memory? Hmm. So the pointers are objects. That's what they were saying there. Because they are variables. That is the format of the variable. Information that can be moved, processed, or stored by a computer. What is this of value? Is the location in memory? Single piece of data is stored in memory. What is a variable? I'm not sure if I know how to define it, but is the piece of data that is stored. Yeah, named region of memory. Identifier is the way that the compile knows the variable that a variable is accessed by. Type is similar to the data, and integer is a number. Oh, yeah. How to interpret a value in memory. So far, it's really basic stuff. So this is new stuff for me. Didn't know that you can initialize variables like that. No, not sure. So assignment copies the value. Initializations both steps at the same time. The brackets is one. Not sure the name, but yeah. Direct base initialization. Mm. So they're gonna talk about it. Not gonna do the programs because I think it's redundant. It's very beginner stuff here that I think I already got it. I'm more interested in the parts that are gonna come short after this, which is the standard library. Hopefully they explain it, how it works behind the scenes. So when you initialize int and it requires the user input, it defines as 0 if they don't put a number. So the fraction is dropped. So the maximum number that a variable can hold is this. Yeah, this brings up a lot of questions because how you do a bunch of calculations if you have to store large numbers into variables. This is very interesting also because how does how's the how does the computer decide or the compiler decide what piece of memory is gonna assign the variable x? I guess it's on the instructions of the language. That is kind of interesting. Initialize variable is when you don't assign any value when you declare the variable, and it's gonna make your program unpredictable. What is undefined behavior and what can happen if you do something that exhibits undefined behavior? You're gonna get unpredictable results. So yeah. So I think this might be interesting to take a picture of, because I have one of these for Python as well. I think for obvious reasons. Yeah, so this helps to avoid mnemonic, I think is the name, mistakes, where or when you're reading a code, when you're reading code for someone else, then you know what variables the programmer assigned, and what variables are actually variables or words are actually from the language itself and not arbitrarily chosen by someone. And this knowing this helps to understand that. This is useful to know as well. It's case sensitive. Yeah, this is previous stuff, I think. But we're summing, so I think this is okay. It's gonna initialize to 0. Correct. Not correct, because this is reserved for OS and libraries and that kind of stuff. Incorrect, because the whole thing is uppercase, should be lowercase when it's only one word. My variable name is incorrect because they either have to be separated by underscore or by uppercase or new letters. Incorrect because it starts with uppercase. Incorrect because it's using a word from the C++, I think. I'm not sure about this one. Yeah, void is a keyword. Correct. This might be okay, but I think it's incorrect because it shouldn't use. Yeah, because tree is a keyword. Now start with a number. Meters of pipe, correct. I think I'm gonna eat something, so I'll be right back. I think I'll watch the Cherno playlist while I eat. Where I stopped.
Hey, what's up guys? My name is Eterno. Welcome to another video. So, I'm on the couch this time. After a long day of work, thought I'd mix it up. Let's talk about variables in C++. So, when we write a program in C++, we want to be able to use data. Most of what programming is about is actually using data. We manipulate data. That's what we do. So any kind of data that we use in our program that we want to change, that we want to modify, that we want to read and write from, we need to store this data in something called a variable. So variables basically allow us to name a piece of data that we store in memory so that we can keep using it. As an example, pretend that you're making a game and you've got a player in your game, and that player character has some kind of position on the map, and the player character can move. So we need to be able to store the player's position as some kind of variable in our memory so that when it comes time to draw the player on the screen or interact with the rest of the level, we can actually see, hey, where on earth is the player? So we would want to store the player's position in a variable. This is basically one of the fundamentals of writing a program in any language. We need to be able to play with data and store that data somewhere. When we create a variable, it's going to be stored in memory, in one of two places, the stack or the heap. Don't worry, we're gonna have a lot of videos discussing how memory actually works, so if you're looking for a more of an in-depth kind of explanation, that'll definitely come. But for now, just know that variables do occupy memory. That's where we actually store the data, in our computer's memory. In C++, we're given a bunch of primitive data types. These primitive data types essentially form the building blocks of any kind of data we store in our program. Each data type that C++ gives us has a specific purpose. Whilst it has a specific purpose, you don't actually have to use it for that purpose. It's interesting because C++ is a very powerful language, which means there are actually very few rules when you actually get down to it. So when I explain variables, I like to say that really the only distinction between the different variable types you have in C++ is the size. How much memory does this variable occupy? When it comes down to it, that's really the only difference between these primitive data types. How big are they? Let's go ahead and jump into Visual Studio and take a look at some examples. So we've actually already got a variable type that we're using here, int. Int stands for integer, and it lets us store an integer in a given range. If we want to declare a brand new variable, we can do so by typing the type of the variable, giving it some kind of name, for example, variable, and then giving it a value. Now this last part is optional. You don't have to give it a value immediately, but for now, let's just give it the value 8. An integer is a data type that is traditionally 4 bytes large. The actual size of a data type depends on the compiler, so it may be different depending on what compiler you're using. Ultimately, it's the compiler's choice to tell you how big a data type is going to be. The int data type is meant for storing integers in a certain range. Because it's 4 bytes large, we are limited as to what kind of numbers we can store with it. Specifically, this is something called a signed integer that can store a value of around -2 billion to +2 billion. Anything larger or smaller than that is going to require more data to store than this int actually supports. So with 4 bytes of data, we can store a value between this range. So let's go ahead and try and print out our
Wonder if they're gonna talk about bitwise manipulation on the book as well. And this concept that he just talked about, it's also a little bit hard to understand, which is that some data types can only hold a certain amount of bits inside of them. So when you want to store larger size, I think that's probably what bitwise manipulation is. Just understanding which data type can hold how many bits. So you figure out different ways to allocate or to design the code so that it is efficient in relationship to the memory that each thing can use. I'm gonna get more food. Right back. One thing that I was just thinking about is that what voltage it really is and electricity, the flow of electrons, is just the nature's tendency of materials reaching some balance and retaining their state, because every molecule and every object is a distribution of the electromagnetic field. So it seems that the universe has this tendency to reach this equilibrium between in energy, and because everything is connected, when you put different objects together, you're increasing the entropy, and the natural state of the universe is to decrease the entropy. And I think this is what generates that voltage and the flow of electricity is nature's tendency to reduce entropy. But since everything is increasing entropy, because everything is moving, and that's what time is, there's this natural dance of the movement of things and their natural tendency to decrease entropy, which makes the universe change itself. So in a way, is this eternal thing where you have movement, which is space-time, and that movement creates entropy, but the natural tendency of the movement is to decrease entropy. There's always the momentum, and then the decretion, I'm not sure if that's a word, of entropy through this tendency of things to reach the energetic balance of the electromagnetic field. So in a way, a black hole is just whatever the resulting momentum of those changes created a region in space-time where you have a great lack of this balance. And that might be what the gravitational field is. Just a tendency for an equilibrium on the electromagnetic state, which creates the attraction between things.
Our variable to the console to see what it actually is. I'll substitute this hello world with this actual variable. This is how we can log a variable to the console. Let's hit F5 to run our program, and you can see it prints out the number 8. Awesome. We can go ahead and modify our variable, for example by reassigning it to something else, like 20. Let's go ahead and print it again and see what happens. So we're printing it once here and then again here. So we should get the value 8 printing first and then the value 20. And you can see if we run our program, that's exactly what we get. Cool. So as I said, an int data type can store a value between negative 2 billion and positive 2 billion. So you might be like, why is it negative 2 billion and positive 2 billion? It's not exactly 2 billion, by the way. It's like 2 point something billion. Where are these limits coming from? Do they make any sense? And the answer is yes, they make sense. They are directly tied with the size of the variable, that is, how much data we're allowed to store in it. An integer is 4 bytes. With 4 bytes of data, we can store values in that range. Let's break this down a little bit. So 1 byte is 8 bits of data, which means that 4 bytes is 32 bits of data. Because this variable is signed, meaning it can be negative, it contains a sign, like a negative sign. Because this variable is signed, one of those 32 bits, has to be for the sign, so that we know if it's positive or negative, which only leaves 31 bits left for the actual number. Now a bit can either be 0 or 1, so there are 2 possible values for 1 bit of data. So using a little bit of maths here, we can say that we have 31 bits to play with, 2 possible values per bit, so what is 2 to the power of 31? If we crack open a calculator here and type in 2 to the power of 31, we will get about 2 billion. That value there, that 2.1 billion, that is the maximum number that we can store with an integer. Now remember, we also have 1 bit that is reserved for whether or not that number is negative. So because of that, we can store up to that number from 0, but also we can go the other way and store all the negative values down to negative 2.1 billion. But I don't want negative values, I hear you say. Is there a way to just get rid of that 1 bit being for the negative sign and just use it as part of my number? Why, yes. Yes, there is. That is what we call an unsigned number. That means it's a number that does not have a sign, meaning it's always positive. In C++, we can make one of those by just typing in unsigned in front of our integer. So now what we've done is we have 32 bits to play with. And 2 to the power of 32, of course, is double what we have here. 4.29 billion. And that's basically what the unsigned keyword does in C++. It lets us define an integer that does not have a signed bit. Okay, so what other data types do we have available to us? What if I don't want a 4-byte integer? What other types are there? So as far as integer values goes, we actually have quite a few. We've got char, which is 1 byte of data. We've got short, which is 2 bytes of data. We have int, which is 4 bytes of data. We have long, which is also usually 4 bytes of data, depending on the compiler. And then we have long, which is usually 8 bytes of data. There's also other types like long int. There are a few different modifications here. I'm not going to go through all of them, but the basic ones are these 5. You can also add unsigned to any of these, and it will remove that signed bit and let you set a larger number. Char traditionally is also used for storing characters, not just numbers. So apart from assigning numbers to it, like 50, you can also assign characters to it, like A. Now that's not to say you can't assign characters to other integers. You can, because at the end of the day, this character that I typed, this letter A, it's just a number. In fact, that number, that numeric value associated with that character, the character A, is 65. Now, if numbers are just characters and if characters are just numbers, then why exactly do we have this distinction? Why do I say that char is specifically used for characters, whereas it's really not? That is because we often, as programmers, make assumptions about certain data types. If I pass in a char and call it something like character, I usually expect you to actually assign a character to it. So a good example of this is if you actually try and print out a char. If I print out this variable, A for example, and I hit F5, I'm not going to get the number associated with it. I'm going to get the character A printed out. So if I replace this with its actual numeric value like 65, I'm also going to get the value A printed out, as you can see over here. Because cout, if I pass in a char into cout, it's going to treat it like a character, not like a number. If I change it to be some other type, like a short for example, and hit F5, you can see that cout no longer treats it like a character. It's going to actually print out the numeric value. And even if I assign a character here, it's just really assigning the value 65. So if I run this again, you can see that we get 65. So the reason I'm telling you all this is because I want you to understand that data types, the usage of data types is just up to the programmer, really. There are certain conventions that we have in place, but there's nothing concrete that you have to actually follow. There are very little rules in C++ after all. So because of that, I do want you to realize that the only real difference between these data types is how much memory will be allocated when you create a variable with that data type. So with those integer types aside, what if I want to store a decimal value, for example 5.5? How do I do that? Well, for that we have 2 data types. We have float and we have double. There are also some modifiers that you can do like long double. We're not going to get into those. So a float is basically a decimal value that we can store that occupies 4 bytes of data. So let's define a variable here such as 5.5. How do we do that? Let's also replace this variable A with printing out our float variable and compile our file. Let's hit F5 to run our program and you can see we get 5.5 printed out. Fantastic. Now you may think that you've defined a float here, but you actually haven't. You've actually defined a double. If we go back to Visual Studio and we hover our mouse over this value, you can see that in brackets it says double. As I just mentioned, we have 2 different variables that we can use to store decimal numbers, float and double. So how do we discern between what a double is and what a float is? The way we do that is by basically appending an F to our float variables. It can be lowercase or uppercase, doesn't matter. But the point is, if we have an F, you can see that we've actually declared a float. So floats are basically 4 bytes large and doubles are 8 bytes large. Finally, we have one more primitive data type to play with, and that is bool. Now bool stands for boolean, and it can either be true or false. If we try and print it to our console and hit F5, you can see that we'll actually get a numeric value, 1. Because of course there's no such thing as true or false. Those are English words. Computers deal with numbers. So basically 0 means false, and anything except 0, any other number, means true. In this case, we'll actually get 1 printing to the console indicating that it is true. If we change this to false and run our program, we will get 0, which means false. The bool data type occupies 1 byte of memory. Now you might be wondering, 1 byte, why? A bool can either be true or false. Surely that only takes 1 bit to represent. And you are correct. It does take 1 bit to represent. However, when we're dealing with addressing memory, that is, we need to retrieve our bool from memory or store it in memory, there is no way for us to actually address individual bits. We can only address bytes. So because of that, we can't actually create a variable type that is 1 bit because we'd need to be able to access it, and we can't. We can only access bytes. Now, of course, one thing you could do on the other hand is be really smart about how you store data and store 8 bools in 1 byte. That's totally okay. 1 bit per bool, but you still have that 1 byte of allocated memory. We'll probably talk about advanced fun tricks like that in the future, but for now, a bool is 1 byte of memory. So with all this talk of sizes and bytes and how much everything takes, how do we actually know how big a data type is? It is dependent on the compiler after all. Is there some way we can check? Yes, there is. There's an operator we have available to us in C++ called size of. So if we come over here and we print size of bool, for example, we basically just type in the word size of and then either in brackets or not, doesn't really matter, although I do prefer to use brackets or parentheses, I should say. We type in our data type, hit F5, you can see it tells us that a bool is 1 byte. If I replace this with int and hit F5, we have 4, and if I do something like double and hit F5, we have 8. Awesome, pretty cool stuff. So that's basically all there is to variables, or at least the primitive types that I've covered. There are many different types that you can actually create in C++ and that have already been created for you. However, they're all custom types that are all based on these primitive types. These are the building blocks that we use to define and store any kind of data we could possibly create. Now, with any of these primitive data types, we also have the ability to turn them into pointers or references. Pointers can be declared by writing an asterisk next to your type like this, and references by an ampersand next to your type. Pointers and references are such huge and complicated and vital topics that I really want to save them for separate videos so that you guys understand them properly. So for now, for this video, we're just going to stick with these primitive types. Make sure you understand them. They're going to be the basis for pretty much everything you ever write, so they're really important. But anyway, I hope you guys enjoyed this video. If you did, please hit that like button. You can also follow me on Twitter and Instagram. And if you really like this video and you want to be a part of how future videos get made, you want to contribute to the planning of these videos, as well as receive early drafts of videos as I'm making them, then please support me on Patreon. The link will be in the description of this video. Your support there is what makes these videos possible. Thanks for watching, guys. I'll see you next time. Goodbye. Hey, what's up, guys? My name is Eterno.
Right back.
Welcome to another video. Today, we're gonna be talking about functions in C++. What? A midweek video? Am I dreaming? Has Cherno gone crazy? Maybe, but that's not the point. I just wanna say a huge thank you for everyone who's enjoying this series. I'm really glad you guys are enjoying this because it's been a real blast to make. If you wanna show me how much you appreciate my videos, you can follow me on Instagram. Link in the description below. Lately, I've been really into photography and it would mean the world to me if you guys could follow me. Just like pause this video right now and just go and follow me. Anyway, back to functions. So what exactly are functions? Functions are basically blocks of code that we write that are designed to perform a specific task. Later, when we get to classes, those blocks are called methods. But when I say functions, I'm explicitly talking about something that isn't part of a class. It's pretty common for us to split up functions to prevent code duplication. We don't want to be writing the same code multiple times. Because of course, if we did, apart from copying and pasting a lot of code and just ending up with this huge mess, it also means that if we decide to change some code, we have to change it in all of those places where we pasted the original code, and that's just going to be a disaster to maintain. So what we can do instead is just write a nice little function that does what we want it to, and then we can call it multiple times in our code if we need to. You can think of functions as having an input and an output, although they don't necessarily need to. We can provide the function with certain parameters, and the function can return a value for us. So suppose that we wanted to multiply two numbers together, and we wanted to write a function that did that. So the first thing I'm going to write here is something called a return value. That is, this is the type that this function will return. Since we're multiplying two integers, that of course will result in an integer. So our return type is going to be int. I'm going to give the function a name, in this case multiply, and it's going to take two parameters. These are actually the numbers that we want to multiply together. I'll just call them a and b. I'll give the function a body, and all this is going to do is return a times b. So you can see that we've got a function here that takes in two parameters, both integers, and simply returns the product of those two numbers. We don't necessarily have to provide parameters. For example, I could just not provide any parameters and return something like 5 times 8. This is still a function that returns an integer, but it's just not taking any parameters. We could also tell the function that we don't want it to return anything, and we do that by writing void as its return type. Void, of course, means nothing. So instead, this could do something like log the result to the console. So let's go back to our original example here where we had int a and int b and we returned the product of those two integers. So how do we call this function? Well, calling a function is pretty simple. Let's go ahead and try and print the result of a multiplication. I'm going to first of all make a variable which holds this result. So I'll type int result equals multiply, and we'll go with 3 and 2. So what this is going to do is call this multiply function with these two parameters, and then store the return value, that is this result of a times b, in this result integer. We can then output that result to the console. Let's hit F5 to run our program, and after it builds, you can see that we get 6, which of course is what 3 times 2 is. So let's kick this up a notch. Suppose that I want to do a bunch of multiplications, and I want to log all of them to the console. If I do something like that without a function, then it would look pretty messy. So for example, I need to repeat this code. So let's go ahead and copy and paste it a few times. I'll call this something like result 2, result 3, we'll do 8 times 5, 90 times 45. And if I run my program and, oh, hang on a minute, why am I getting the same value everywhere? Oh look, when I copy and pasted this code, I forgot to change the variable. Now you may have thought that I did that by accident, but I actually did it on purpose to prove something. This actually happens all the time. People copy and paste blocks of code and then forget to change one minor detail. And in certain situations, you might actually just run your program and not even notice that it's not working correctly until it breaks somewhere down the line. And yet something like this can actually be fixed really easily if you just create a function for it. So let's go ahead and fix this by actually printing out result 2 and 3. If I run this, we will get our correct results, which is great. However, you can see that I'm actually calling this multiple times and it's just a little bit annoying. Like for example, further down the road, if I decide to replace this multiply function by simply doing something like 8 times 5, look at this, I have to replace it in every single place. 3 times 2, 90 times 45, I don't want to have to deal with that. So this multiplication and then logging the result, let's go ahead and make a function for that. It'll be void because it's not really going to return anything to us, it's just going to perform what we ask it to do. We'll call it something like multiply and log. And then let's take a look at which parameters we might want. So what actually changes between these 3 blocks of code? The values that we actually multiply, that's it. So those become the parameters for our function. What actually changes between these blocks of code? What needs to be specified for this function to perform its job? Let's go ahead and write in our parameters. So we're going to be taking in two integers, a and b. You can really call them anything you want, but a and b seems sensible. We'll copy and paste one of these blocks into this function. This looks pretty good. Of course, I'll replace 3 and 2 with our parameters so that we're using the parameters we specify into this function to perform the multiplication against, which will cause a times b to get multiplied here. And then we're going to be logging our result to the console. So now, instead of doing this so many times, all I have to do is simply call multiply and log with my parameters. So 3 and 2, for example. And then we have 8 and 5. And then we have 90 and 45. And that's it. Look at that, I can get rid of all of this code and this is what we end up with. A nice, clean, and easy to read program. If I launch my program, you can see that we get the correct values here. So this is a pretty simple example, but I think it's effective in demonstrating that functions are really, really important. You should be aiming to split up your code into many, many functions. However, one thing that I want to stress is don't go overboard. You don't need a function for absolutely every line of code. That's not going to be good for anyone. It's going to be hard to maintain, your code's going to look messy and cluttered, and it's actually going to make your program slower. Every time we call a function, asterisk, the compiler generates a call instruction. What this basically means is that in a running program, in order for us to call a function, we need to create the entire stack frame for the function, meaning we have to push things like the parameters onto the stack. We have to also push something called a return address onto the stack. And then what we do is we actually jump to a different part of our binary in order to start executing the instructions from our function. And that return value that we push, we need to get back to where we originally were before we called the function. So there's this whole like jumping around memory in order to execute function instructions, and all of that takes time. So it slows down our program. Now the reason I said asterisk earlier was because this is all assuming that the compiler decides to keep our function as an actual function and doesn't inline it. We're going to talk in depth about inlining in a future video. So the reason I'm saying all this is because you don't want to just go ahead and create a function for absolutely every line of code. Don't be ridiculous about it. It takes a little bit of experience to realize what you need a function for, but basically if you see yourself doing a common task multiple times, create a function for that. The primary point of functions is to prevent code duplication. We don't want to just be copying and pasting code everywhere. Now, if we go back to our code for just a second, you might have noticed something a little bit odd about this main function. It says that its return value is int. However, the return keyword is nowhere to be found, and I'm obviously not returning anything. So if I specify a return value, do I actually need to return something? Let's go ahead and try and just do nothing in this multiply function. I'll hit Ctrl F7 to compile my file. Look at this, I'm getting an error telling me that multiply must return a value. So do functions with a return type actually need to return values? The answer is yes, they do. The main function is actually a special function. The main function, and only the main function, is exempt from this kind of must return a value. If you don't specify a return value, it will automatically assume that you're returning 0. So it will be identical to if I had written this. This is just a feature of modern C and C++ versions that lets you just keep your code a little bit cleaner. And just for fun, know that this must return a value thing is actually something that only applies in debug mode. If we compile in release mode here, you'll see that we actually don't get an error. That's not to say that what we're doing here is correct, because if we actually do capture that return value and decide to do something, we will get undefined behavior. It's just that the compiler won't actually yell at us. However, in debug mode with certain debug compilation flags enabled, we will get an error, which will just help us debug our code. Because at no point should you be writing a function that says it's going to return something but doesn't. Okay, so that's pretty much a basic introduction to functions. Functions are really useful. I'm going to be writing a lot more of them in the future. Every program is built from a collection of functions, so this is really important stuff. If you don't think you fully understand how functions work, don't worry, because throughout this series we're going to be writing so many functions that you're just going to get used to it. And the best way to learn is, of course, to practice. We also commonly break up functions into declarations and definitions. So declarations we usually store in header files, and then definitions we write in translation units or CPP files. Soon I'm going to make a whole video dedicated to header files, and we're going to cover function declarations in header files in that video. But anyway guys, I hope you enjoyed this episode. If you did, please hit the like button. Don't forget to follow me on Twitter and Instagram. And if you really enjoyed this video and you want to see drafts of future videos early, as well as discuss what actually goes into these videos, you can support me on Patreon. Link will be in the description below. But until next time guys, goodbye. Let's go somewhere fun today. Alright, let's try something new. Hey, what's up guys? My name is Eterno. Welcome back to my C++ series. So today, header files, and we're actually out. Started off as a great day, then it started raining, but I decided to get out of town because, so we're here somewhere in Australia, and we're going to be talking about C++. I hope you guys don't start to think that header files are so boring that I felt the need to just get out of town to cover them. That's just what I just felt like doing. Alright, so header files, what are they? Why do we need them? Why do they even exist in C++? A lot of other languages that you might have been used to, like Java or C#, they don't actually have header files or any kind of concept of two different file types, where we have our compilation file that we actually compile, like a C++ file, a translation unit, and then we also have a header file, which is just this weird kind of file that we always include in places, and why is it even there? Header files are actually much more useful, and they're used for much more than just to kind of declare certain declarations that you want to use in multiple CPP files. And as this series kind of goes on, we're just going to learn so many new concepts that really do require header files in order to work, so don't dismiss them too quickly. As far as the basics of C++ goes, header files are traditionally used to declare certain types of functions so that they can be used throughout your program. If you think back to my C++ compiler and linker videos, I talked about how we need certain declarations to actually exist so that we know what functions and types we have available to us. For example, if we create a function in one file and we want to use it in another file, C++ isn't going to know that that function even exists when we try and compile that other file. So we need a common place to kind of store just declarations, not definitions, because remember, we can only define a function once. We need a common place to store declarations for functions, just declarations, no actual definitions, no body for the functions, but just a place that says, hey, this function exists. Let's take a simple example here. So suppose that I have a function here called log that is supposed to log something to the console. It's going to take in a const char message, and it's going to simply see out that message. If I then go ahead and create an additional file, we're going to call this log.cpp, and then maybe that additional file has something that initializes our log and decides to log something to the console, we're going to get an error because this log function doesn't actually exist in this file. This file doesn't know about the log function. Of course, back in main, here it is. The log function exists fine, and we can actually replace our hello world logging to use that log function. And if I try and compile my program by hitting Ctrl F7, you'll see that it works fine and we don't get any errors. However, back in log, if I try and compile this, we get an error. Because of course, as far as this file is concerned, log doesn't exist. So what does log.cpp actually need in order to not error us? How do we tell it that that log function does actually exist, but it's just defined elsewhere? That is where a function declaration comes in. If we go back to our code here, I need to simply declare that log does exist. If we go back to main and we take a look
So
at...
pretty much the purpose of a header file is so you don't have to import a bunch of libraries every time you create a new file. You can just import header and then everything is there. It's more organized. I think I get it now. I'm gonna go brush my teeth. Be right back.
this actual signature, you'll see that log is a function that returns void and takes in one parameter, which is a const char pointer. And some child is chasing the kangaroos. That's funny. So this is the function's signature. We can literally just copy this, go back to log.cpp, paste this in, and just close it with a semicolon. The fact that this function doesn't actually have a body means that it is the declaration of the function. We haven't defined what the function actually is, what the function actually does. We've just said, hey, there's a function called log that returns void and takes in a const char pointer. That function exists. You can see that our IntelliSense error has gone away, and if I hit Ctrl F7, we do compile. And if I right-click on Hello World and click Build to actually build my program, you can see that it links fine as well, because it's found that log function. All right, fantastic. So, great. We've found a way to actually tell our log.cpp that log function exists somewhere. But what if we make another file? What if I make some other file that needs to use this log function? Does that mean that I also have to copy and paste this void log declaration everywhere I go? The answer is yes, you actually do need to do that. However, there is a way to make that easier. Header files. Right? What are header files? header files traditionally, I should say, because really this is C++. You can do anything with anything. But header files are usually files that get included into CPP files. So basically what we do is we copy and paste the content of header files into CPP files, and we do that via the #include preprocessor directive. So #include has the ability to copy and paste files into other files, and that is exactly what it seems that we need to do here. We need to copy and paste this log declaration into every file that needs to use that log function. So let's have a go at making a header file. I'm going to right click on header files. Now note these folders here are called filters. They're not actual real folders. I can create a header file under source files. There's going to be a few videos on how Visual Studio works in the future, but for now just know that these are kind of fake folders. It doesn't matter which one you right click on to create your header file. I'm going to create it under header files because that makes sense, but it doesn't really matter. I'm going to make a header file called log.h. You'll notice that it's straight away inserted some code for me automatically that says #pragma_once. We'll talk about that in just a second. So here I'm going to put in my declaration. I'm going to cut my declaration from the log.cpp file and put it into here, into my header file. So now the idea is this header file, log.h, I can include everywhere where I want to be able to use log. And of course, it's going to do for me what I didn't want to do manually, and that is copy and paste this everywhere throughout every file that requires it. I don't want to have to do that copying and pasting myself, so I've basically found a way to kind of make it look a bit tidy and automate it to some extent. So back in log.cpp, you can see we get an error now because we're not actually declaring that function. However, if I type in #include log.h, check that out. We don't get an error and our file compiles. Fantastic. What we can also do is actually include it into main.cpp. Now main.cpp contains the actual definition for the function, so it doesn't really require it. We can call log anyway, but just so you know, it's not going to hurt for us to actually include log.h into here and compile. That's not going to be a problem. Alright, so back in log.cpp, you can see we've defined this fantastic function called initlog. However, no one actually knows about it except for log.cpp. If I want to be able to call it from main, I'm going to need that declaration. If I call initlog over here, it's going to give me an error because that's not declared anywhere. So let's go ahead and add that function signature initlog into our log header file, just like that. Fantastic. Make sure that it matches the function signature that you've actually declared in your CPP file. So now everything seems well in the world. I'm also going to go ahead and cut and paste this log definition into my log file because that makes a lot more sense. Now I get an error here telling me cout is not found. That's okay. I can just include IOStream. Awesome. So back in main, if I run my program, we can see that we managed to initialize our log and then log hello world to the console. Fantastic. All right, brilliant. So let's go back to that header file and take a look at what that pragma_once statement actually was. So here we have a statement that Visual Studio has seemingly inserted for us called #pragma_once. What is this? So firstly, anything that begins with a hash is known as a preprocessor command or a preprocessor directive. It means that this is going to be evaluated by the C++ preprocessor before this file actually gets compiled. Pragma is essentially an instruction that is sent to the compiler or to the preprocessor. And what pragma_once essentially means is that only include this file once. So pragma_once is something called a header guard. What it does is it prevents us from including a single header file multiple times into a single translation unit. Now I chose my words there very carefully because you have to understand that it does not prevent us from including our header file into multiple places in our program, just into a single translation unit. So a single CPP file. The reason is that if we accidentally include a file multiple times into a single translation unit, we can get duplicate errors because we'll be copying and pasting that entire header file multiple times. One of the best ways to demonstrate this is if we were to create a struct, for example. If I create a struct here called player, I can leave it empty, it doesn't really matter. If I were to include this file twice into a single translation unit with no header guards, it would actually include that file twice, which means that I would have two structures with exactly the same name, player. We can take a look at this example by commenting out our pragma_once, and then back in log, I will include log.h twice. If I try and compile my file, you can see that we get a player struct redefinition error because we're redefining that struct player. We can only define one struct called player. Structs need unique names. So again, you say, Cherno, why would I do this? I'm not a stupid programmer, I'm not as dumb as you think. Why would I include a file twice? Well, young one. This comes back to how include works. Remember how include works is it copies and pastes files into other files, meaning you can create a bit of a chain of includes. So you could have a header file called player, which includes log, then player is included in some other file, and then maybe that third file contains every include. So if I create another header file here called common, common is just going to contain some common includes. For example, it will include log. If I go to log.h and make sure that pragma_once is commented out, and into log.cpp I include log.h and common.h, if I compile my file, guess what? I still get that error, because that struct player is being redefined. If we were to resolve what the preprocessor actually did, you could see that it actually has included log twice. However, back in log.h, if we get rid of that comment and try and compile our file, we don't get an error, because it recognizes that log has already been included and it does not include it twice. Now there is one other way that we could add a header guard, and I actually kind of like this for teaching purposes because it makes a little bit more sense than some kind of pragma_once, although pragma_once does look a lot cleaner. The traditional way to add header guards is actually via an if-def. So what we can do is we can actually type in an if and def, and then we can get it to check some kind of symbol, for example, log h. We're going to define log h, and then at the very end of our file, we're going to type in andif. So what this is going to do is first of all check to see if a symbol called log h is actually defined. If it's not defined, it's going to go ahead and include the following code in compilation. If this was defined, then none of this will be included. It'll be all disabled. So once we do pass this initial check, we're going to define log h, which basically means that next time we go through this code, it will be defined, so it will not be repeated. A really easy way to demonstrate this is just to copy and paste this entire file into our log CPP file. And then if we take a look at this, I'll also comment out log.h and common.h. So you can see over here that the first time, this is all fine. It includes the file and everything's okay. And then the second time, it's all grayed out because log.h has already been defined. So this kind of header guard is something that was used a lot in the past. However, now we have this new preprocessor statement called pragma once. And so we mostly use that. It doesn't matter which one you use to some extent, although pragma once is a lot cleaner, so it's something that I personally use, and it's something that most people do use in the industry. Pretty much every compiler now supports pragma once, so it's not like a Visual Studio only thing. GCC, Clang, MSVC, they all support pragma once, so don't be afraid to use it. That being said, if you do find legacy code or just code that people have written using different styles, you may encounter this if-and-def header guard, so just be wary of what it is. But again, I would never write if-and-def, I would always use pragma once. The last thing I want to show you is with header guards, we have this kind of discrepancy between include statements. Some include statements use quotes, some include statements use angular brackets. What is the deal? The deal is actually pretty simple. They mean two different things. When we compile our program, we have the ability to tell the compiler of certain include paths. These are basically paths to folders in our computer that contain include files. If the include file that we want to include is inside one of these folders, we can use angular brackets to tell the compiler to search our include path folders. Whereas quotes, on the other hand, are usually used to include files that are relative to the current file. So for example, if I had a file called log.h that was up one directory from this current log.cpp file, I could use .. to go back, and that would actually go back to a directory because this is relative to this current file. Whereas with angular brackets, they are never relative to this current file. They just have to be in one of the include directories. We'll talk more about setting up include directories and all that in the future. I don't want to complicate things too much, but that's basically the gist of how this works. Now, quotes can also be used to specify files that are relative to include directories that are passed to our compiler. So you can actually use quotes anywhere. I could replace this IO stream to be in quotes, and it would totally work. So angular brackets only for compiler include paths, quotes for everything. However, I usually like to use them just for relative paths, since you might as well use the angular brackets for something. Alright, final thing for today. One other thing that you might notice is this IO stream doesn't actually look like a file because it doesn't contain any extension. It's just called IO stream. What's up with that? Well, it actually is a file. It's just that it doesn't have an extension. This is something that whoever wrote the C++ standard library decided to do, to basically separate out C standard library header files and C++ standard library header files. Header files that are in the C standard library will often have a .h extension on the end. However, C++ files do not. So this is just one other way you can differentiate between what is in the C standard library and the C++ standard library, whether or not it has that .h extension. IOStream is a file just like anything else. In fact, in Visual Studio, if we right-click on it and hit Open Document, you can see that it takes us to this IOStream header file. And if we right-click on it on this tab here and hit Open Containing Folder, you'll see where it's actually located on our computer, inside this directory. And here it is, that IOStream header file. Alright, so that's it. Header files, pretty easy. We're going to be using this extensively in this series, so there'll be plenty of examples to follow. You'll see how I use them, you'll see how you should be using them, but you should now understand how they work and what they're used for. So anyway, I'm going to get out of here because it's getting really, really cold, but I hope you guys enjoyed this video. Let me know what you think of this whole,
It goes a lot deeper than the Code Academy stuff covers. A lot deeper. No wonder why there's hundreds of videos from these people explaining the stuff, which is cool, but also challenging at the same time. I think I'm gonna read for 2 more hours here for today, and I think reading this stuff is gonna be a very good way to, because I still have a bunch of stuff that I need to finish off stream and to study. So while I do that, I think I'm gonna read this whole thing on stream. And then only after I read this stuff, which it's probably gonna cover all these questions here, the easier ones. Then I'll continue to go through the list of steps. So I'm probably gonna read this every day, until I finish it. So yeah, I might. The other days where I'm gonna read this, I'm going to read out loud. I think it's gonna be better to memorize. Maybe read some parts out loud, and some parts just listening to music if I get tired. I prefer this one instead of this. It's not opening up my thing. It's probably already set up. 7. It's true. 14. Expression has an output and a statement, and not necessarily. Yeah. Doesn't contain. Doesn't contain. Contains. Oh yeah, just assigning the value of 5 to x. So I guess it is an expression. It is expression as well, but it's probably the wrong way to do it. I would say it's an expression. So first it's going to print 5. It's going to initialize 6 to x. Y to x minus 2, which is going to be 4, but it's going to be discarded, I think. So I'm not sure if it's going to print 4 here or not. Then initializes 0 as z with 0. That makes it equal to the value of x. and it's gonna return 0 here. So 5, got it correct. Then returns 4 and 0. Okay. So it does return a value here, even though it discards the value after it initializes y. I guess it runs the expression every time you call y. What is wrong here? Should initialize the number 4, maybe? The count. So the arrow is the problem. So it would be the same line, but with same line that was done here, but with times 3. Num times 3. Using the same input, I guess. Yeah. Not that difficult. I'm going slightly fast through this because it's easy stuff, I guess. This is a question I had. I guess I erased. So this is a solution for scope of variables, because this function, if you don't do this, then the main can't have access to the return value of this function. But if you initialize a variable inside the scope of main with this function, then the return value of this function is going to be stored inside of this variable, which is going to make the main function have access to the scope of that variable, which is useful to know. So we can put these two parts in a function and then store that on another variable, and then call the function twice. But then I wonder what would you do? Yeah, I think each time that you want to call the function, you would initialize it to a different variable, and then you would do the same thing. X, Y, yeah. 16. The dentation is incorrect here, but C++ doesn't care apparently. So I think you return 16. No, actually it's not correct because this is actually declared inside of this function. I didn't see it. I thought it was just a indentation, so it doesn't compile. 7, 9. This calls twice, but it doesn't initialize, so it's not going to return anything on main because of the scope. Any output. This prints twice because void doesn't have any return. But I'm not sure, it may not compile, but I think it prints twice. Yeah. Prints does not compile. So you can't put the standard count here. Interesting. Doesn't make sense at all. Oh, so it works. Yeah, but it only prints 5. I thought you couldn't do this. I thought you would throw an error. I guess I don't think this works. Yeah. Doesn't work because it doesn't have the parenthesis. Don't repeat yourself because you want to decrease the chances you make a mistake. And so far, I'm on the very beginning. It's kind of a lot of the things are redundant, but I learned a couple, maybe 1 or 2 things, or yeah, around 5 things, between 2 and 5 things, new things that I didn't know before. And the redundant parts are good for remembering stuff, but nothing really. I think they're gonna talk about the IO stream library soon. I'm trying to go a little bit faster to this part because so far it's a bunch of things that I have already seen with very few exceptions. Oh, so I get it. It's gonna return input, and then it's gonna call print double with input. So this is also useful to know. The order of importance is not always the same. It depends on the design. So if one function needs to be called before the other, you should specify it by calling the name with var afterwards. Yeah, so it doesn't matter actually which order. It's just best to not rely on the order of the functions. If you're gonna pass parameters, if you're gonna pass functions as parameters, yeah, so this part is important, but it's just talking about stuff that I already know. When you declare variables in a local scope, inside of the function, there you have local scope, which means that the program overall is not going to have access to them, only the function that is using them. And when you declare variables outside of the scope, these functions inside main, let's say, which is the function that you need to put in every program, then all the other functions are going to have access to them, but they're going to be stored in a different place in memory. And I think it's usually best practice to have the least amount of global variables as possible, because the allocation of memory using global variables is not that efficient. But I'm not 100% sure about that. because of the scope. So I think here int main has access to 5 and 6, and when you call here add 5 and 6, you still have the value of this. Yeah, so these variables are only referred to the add function and this to the main. So they have these different scopes, although they have the same names. So they are assigned to different places in memory. I think this is starting to get a lot more clear to me. I'm curious about when they start talking about pointers though, because pointers are very confusing. This keyword and for JavaScript and self for Python, and the special characters for C++. I think those are the hardest ones to understand. But it's getting easier and easier every time I read or see them. It's all about memory allocation and understanding the way that the program is compiled into machine code so that you know the path, the flow of information through the execution. And the main logic which every language uses, which is if statements, for loops, objects and functions, pretty much, and then classes. I think one of the questions I have is just reading the other pages, not when necessarily when to use functions, but what's the time to create another file? How do you make the decision of creating other files? And so far, I think the way I intuitively organize myself is whenever I create a file for specific tasks. So whenever the task starts to deviate from the initial purpose, then I just separate the code and put it in another file. So each file has kind of a theme around them. But I'm not necessarily sure that if that's the best practice. So this is because of the execution. Add is declared after, so I guess main doesn't find add. I think this is different than other languages because the other languages would probably run because they would just find the function, but I'm not sure as well. So yeah, just put the function on top. And that's when the header file it's gonna start to come in, I think, here. This function declarations. So they are always declared on top when you use the header file. I guess I'm gonna do this just so I remember. That's easy. Source files. It's super easy. think I'm actually gonna stop here. I think this is a good place to stop. I'm kind of tired, and I think this is the part that I wanted to know when I started reading this book, which is gonna be namespace and standard libraries. So I think this might be better to leave another day. So yeah, I think I'm not sure if I'm gonna read the whole book line by line. I might just fast read through the parts that I'm not sure if it's gonna be repeated or too redundant. And then on the parts that I think that might be something that I'm trying to understand and I didn't, I might slow down and read it. But I'll probably do that next times, and then I'll continue doing the steps on the other file. So see you then.